Let us start chapter 6, module 1. In this module, we shall discuss a way of forming new topological space from old one. We have already discussed some ways to form new topological space from old ones. For example, construction of subspace. For example, product topologies. In all these, we construct new topological spaces from old ones. As we have seen in the case of group that we can form new algebraic structure or new group from old ones. Let us recall that if H is a normal subgroup of a group G, then G by H is a new group called quotient group of G. In that way, for any given normal subgroup, we can construct new group. Same holds also for ring. We can form new rings from old ones. This type of group generally called quotient group. For example, if can consider R by Z, where Z is a subgroup of R. Since R is commutative, so Z must be a normal subgroup. R by Z is a new group formed from R. This is called quotient group of R. In case of topological spaces, we can also form new topological spaces which are called quotient spaces. In case of quotient group, we have seen that if H is a normal subgroup of G, then the set of all left cosets form a partition of G, and then we give a group structure on that partition using the group structure of G. In case of topological spaces, we also take partitions and use the topological structure of X to give a new structure on that topological spaces. This way, we can form lots of new topological spaces. For example, let us consider Mobius strip. What is Mobius strip? Let us take a rectangular sheet and let us identify the two sides in the opposite direction. The new topological spaces formed in this way is called Mobius strip. Now, if we identify these two sides without the orientation reversing, then the space is formed called cylinder. Let us take a rectangular piece of paper. We can identify left side and right side, and then we can identify upper side and lower side. In this way, we can form torus, which are clear intuitively. We have to formalize this using mathematical notions. For this, what we will do? In fact, we shall take a partition on the topological space X. Now, we shall consider the natural projection map from X to partition set. Now, we will declare a subset of that partition set as open if and only if its inverse image in capital X is open. Note that here open is not in the sense of topology. Here this open is just only the name. But we can prove that the sets open in this way forms a topology on that partition set. This topology will be called a quotient topology. For further discussion, let us pass to slide presentation. I have already discussed about the formation of quotient space from a given topological spaces. I have told that cylinder or Mobius strip can be formed from a rectangular piece of rectangles by identifying the left side and right side either in orientation preserving way or orientation reversing way. Now, I have to give the formal definition of quotient space or identification space. Let X be a topological space and let capital Y be any set obtained by partitioning capital X. Suppose P from capital X to Y is the natural quotient map. Let us declare a subset G of Y as open if and only if P inverse G is open. Then the collection G subset of Y such that F inverse G is open in capital X is a topology on capital Y. This topology is called quotient topology on Y induced by P. When capital Y is endowed with such a topology, then this is called quotient space of X and the mapping P is called quotient map. But here we have to verify that the collection G subset Y such that F inverse G is open is in fact a topology. Let us give it as an exercise. Now we shall give some characterization of quotient mappings. Let capital Y be a quotient space defined as above and capital Z be an arbitrary topological spaces. Then a function f from y to z is continuous if and only if the composite map f compose p is continuous. To prove this, let f compose p be continuous and a subset of y be open. Then f composition p inverse of a is open in X, but f composition p inverse of A is equal to p inverse of f inverse of A. Since Y is quotient space, therefore p inverse of f inverse of A is open whenever f inverse A is open. This shows that f is continuous mapping. The converse part is obvious since composition of two continuous mapping is continuous. Next, we like to define quotient map or identification map. A continuous surjective map F from a topological space X to a topological space Y is said to be a quotient map if the topology of capital Y is largest, which makes the mapping F continuous. In fact, if we consider a surjective function f from capital X to Y, then we get a partition of capital X whose members are subsets of the form f inverse of Y, where Y belongs to capital Y. Now consider the quotient space associated to this partition as y star and let P from x to y star be the canonical map. Now, if we can prove that y and y star are homeomorphic, then the reason for the terminology quotient map will be justified. So, we are in a way to prove that y and y star are homeomorphic. First, we need the following. Let f from x to y be a quotient map. That means f is a continuous surjective map from x to y, and the topology of y is the largest topology which makes f continuous. Then y and y star are homeomorphic. In addition to that, a function phi from y to any space z is continuous if and only if the composition phi compose f is continuous. To prove this, let us consider the points of y star. These are just the fibers f inverse of y, which are corresponding equivalence classes. Now, we define the mapping from y to y star by putting y goes to f inverse of y, that is corresponding fiber. This gives us required homeomorphism. For the second part of this theorem, let phi compose f be continuous and a subset of z be open. We have to prove that phi is continuous. That means we have to show that phi inverse of a is open, but we have given that phi compose f of inverse of a is open in capital X. Now consider the following equality: phi compose f inverse of a is equal to f inverse of phi inverse of a. Since f is a quotient map and f inverse of phi inverse of a is open, we have that phi inverse of a is open. This proves that phi is a continuous mapping. So far we have discussed about quotient spaces and quotient mapping, and also we have given some properties of quotient mapping. We have observed that quotient mapping are always continuous surjective map. So the natural question is that whether quotient mappings, whether all continuous surjective maps are quotient maps. We shall see in an example that not all continuous surjective maps are quotient maps. We shall also provide some sufficient condition of being quotient maps. Let us go to slide presentation. So, I am giving an example of a continuous surjective map which is not a quotient map. Consider the map P from semi-open interval 0, 1 to unit circle S1 where 0 is open. The mapping is defined by P of x is equal to e to the power 2 pi I x. Then observe that P inverse of minus 1 to 1 arc on S1 is equal to the interval minus half to 1 where the left hand side is open and right hand side is closed. That means that minus half to 1, this is open, but the arc minus 1 to 1, minus 1 is open and 1 is closed, is not open. Hence, we have a set of the form that P inverse A is open but A is not open. That means that P is not a quotient mapping. Next, we shall give a sufficient condition for being quotient map. We know that quotient map must be continuous surjective. Now, if a continuous surjective map is either open or closed, then it will be a quotient map. For this, suppose f from x to y maps open sets to open sets. That means f from x to y is an open mapping. Now, let u be a subset of y for which f inverse of u is open in x. We have to prove that u is open in y. Since f is surjective, we have that f of f inverse of u is equal to u. Therefore, u must be open in the given topology of y. So, this topology is the largest for which f is continuous and thus f is a quotient map. The proof for closed map is also similar. Next, we present an example of a quotient mapping. In fact, this example is a modified version of our previous example. We consider the mapping P from closed unit interval 0, 1 to the unit circle S1 defined by P of x is equal to e to the power 2 pi I x. Then P is clearly a continuous surjective map. Now, to prove that P is a quotient mapping, it is sufficient to show that P is a closed map. Now, since 0, 1 closed interval is compact, every closed subset of closed interval 0, 1 is compact, and as P is continuous mapping, so its image under P is compact, and S1 being housed off, we have that the image is closed. This shows that P is a closed mapping and therefore P is a closed continuous surjection, which shows that by previous lemma that P is a quotient map. In fact, under this map 0 and 1 have been identified. Quite similarly, we can prove that torus is formed from I cross I by identifying left side and right side and upper side and lower side. In fact, we can define torus as S1 cross S1 with the usual product topology. Now, we like to visualize torus as a quotient space of I cross I by identifying 0t with 1t and S0 with S1, where both t and s are from 0 to 1. If we first identify the top and bottom edges of the rectangle, we obtain a cylinder, and then identifying two ends of the cylinder, we get a torus. The identification of opposite edges of the rectangle forces all four corners to be identified to a single point. Since 0 0 is identified with 0 1 is identified with 1 1, this implies that 0 0 is identified with 1 1. Here the identification map is defined as P of xy is equal to e to the power 2 pi I x, 2 pi I y. Like the previous example, P being continuous surjective map, and as I cross I is compact and S1 cross S1 is Hausdorff, we have that P is a quotient mapping. Next, we shall prove that quotient space dn by Sn minus 1 is homeomorphic to Sn. Let us first try to visualize it for D2. Before that, let us make a convention that if X is a topological space and A is a subset of that topological space, now if we identify the whole subset A to a single point, then we shall write the quotient space as X by A. Following this convention, if we identify the boundary of D2 to a single point, then we shall write it by D2 by the boundary, where the boundary is S1. Therefore, if we identify the boundary S1 of D2 to a single point, then we shall write it as D2 by S1. It is easy to visualize that D2 by S1 is in fact a sphere, but we have to make mathematical formulation. For this, let us consider the unit disk Dn in the Euclidean space Rn. Then its boundary is homeomorphic to Sn minus 1. Now, if we identify the whole Sn minus 1 into a single point, then the corresponding quotient dn by Sn minus 1 will be Sn, which we wish to prove. This is not very surprising for the case n is equal to 2 to visualize. Now, to give the formal proof, let us construct a map F from Dn to Sn, which is onto 1 1 on Dn minus Sn minus 1, and which identifies all of Sn minus 1 to a single point. Then this is a quotient map by previous results, and so we get our required homeomorphism. Since we know that Rn Dn minus Sn minus 1 and Sn minus North Pole are homeomorphic, we can choose specific homeomorphisms H1 from Dn minus S1 minus 1 to Rn and H2 from Rn to Sn minus North Pole, and then define Fx by the formula Fx is equal to H2 multiplication H1 of x when x belongs to Dn minus Sn minus 1 and Fx is equal to North Pole when x belongs to Sn minus 1, then it can be proved easily that f is continuous. This f gives our required homeomorphism that dn by Sn minus 1 is homeomorphic to Sn. We end this section by mentioning an important quotient space which we shall call real projective plane and which will be denoted by Rpn. To do this, let us consider the Euclidean space Rn plus 1 minus origin. Now we consider an equivalence relation on this space by defining that x is related to y if and only if x is equal to yr for some real number r. Then the corresponding equivalence classes are lines passing through origin. Now if we take the quotient topology induced by the natural projection mapping from the Euclidean space minus origin to this corresponding partition set, then we get a new topological space which is a quotient space obtained from Rn plus 1 minus 0 is called real projective plane. It can also be viewed as the quotient space obtained from Sn by identifying diametrically opposite points. With this, we end this slide presentation. To conclude this module, let us summarize what we have learned. We have learned quotient spaces, quotient mappings, and some examples of quotient spaces. Very important quotient spaces are unit circle, which is obtained from the closed unit interval 0, 1, torus, which is obtained from I cross I, the quotient space dn by Sn minus 1, which is homeomorphic with Sn, and real projective plane. With this, we end this module. Let us pass to the next module.